ever since NASA's Voyager 1 spacecraft flew past Jupiter in March 1979, scientists have been baffled by the existence of lightning on Jupiter. Now, thanks to the Juno craft, the mystery has been solved, and it turns out Jovian lightning is far more similar to Earth's than thought. It comes as NASA also revealed it was extending the life of the Juno probe by 3 years, keeping it in operation until 2021. Voyager's data showed that the lightning-associated radio signals didn't match the details of the radio signals produced by lightning here at Earth. In a new paper published in Nature today, scientists from NASA's Juno mission describe the ways in which lightning on Jupiter is actually extremely similar to Earth's lightning, in most ways. No matter what planet you're on, lightning bolts act like radio transmitters, sending out radio waves when they flash across a sky, said Shannon Brown of NASA's Jet Propulsion Laboratory in Pasadena, California, a Juno scientist and lead author of the paper. But until Juno, all the lightning signals recorded by spacecraft Voyagers 1 and 2, Galileo, Cassini were limited to either visual detections or from the kilohertz range of the radio spectrum, despite a search for signals in the megahertz range. Many theories were offered up to explain it, but no one theory could ever get traction as the answer. Juno, which has been orbiting Jupiter since July 4, 2016, used its suite of highly sensitive instruments, including the Microwave Radiometer Instrument (MWR), which records emissions from the gas giant across a wide spectrum of frequencies. In the data from our first 8 flybys, Juno's MWR detected 377 lightning discharges, said Brown. They were recorded in the megahertz as well as gigahertz range, which is what you can find with terrestrial lightning emissions. Juno gets a life extension. Why will NASA's probe now operate until 2021? NASA has approved an update to Juno's science operations until July 2021. This provides for an additional 41 months in orbit around Jupiter and will enable Juno to achieve its primary science objectives. Juno is in 53-day orbits rather than 14-day orbits as initially planned because of a concern about valves on the spacecraft's fuel system. This longer orbit means that it will take more time to collect the needed science data. An independent panel of experts confirmed in April that Juno is on track to achieve its science objectives and is already returning spectacular results. We think the reason we are the only ones who can see it is because Juno is flying closer to the lighting than ever before, and we are searching at a radio frequency that passes easily through Jupiter's ionosphere. While the revelation showed how Jupiter lightning is similar to Earth's, the new paper also notes that where these lightning bolts flash on each planet is actually quite different. Jupiter lightning distribution is inside out relative to Earth, said Brown. There is a lot of activity near Jupiter's poles but none near the equator. You can ask anybody who lives in the tropics, this doesn't hold true for our planet. NASA says heat is the key to the difference. Earth derives the vast majority of its heat externally from solar radiation, courtesy of our sun. Because our equator bears the brunt of the sunshine, warm moist air rises through convection more freely there, which fuels towering thunderstorms that produce lightning. Jupiter's orbit is 5 times farther from the Sun than Earth's orbit, which means that the giant planet receives 25 times less sunlight than Earth. They do provide some warmth, heating up Jupiter's equator more than the poles, just as they heat up Earth. Scientists believe that this heating at Jupiter's equator is just enough to create stability in the upper atmosphere, inhibiting the rise of warm air from within. The poles, which do not have this upper-level warmth and therefore no atmospheric stability, allow warm gases from Jupiter's interior to rise, driving convection and therefore creating the ingredients for lightning. In a second Juno lightning paper published today in Nature Astronomy, Ivana Kalmaova of the Czech Academy of Sciences, Prague, and colleagues, present the largest database of lightning-generated low-frequency radio emissions around Jupiter whistlers to date. The dataset of more than 1,600 signals, collected by Juno's WAVES instrument, is almost 10 times the number recorded by Voyager 1. Juno detected peak rates of 4 lightning strikes per second similar to the rates observed in thunderstorms on Earth, which is 6 times higher than the peak values detected by Voyager 1.